Okay, let's start. Good morning, everybody. I hope everybody is well. Today we will talk about current, resistance, and also electromotive force. I will try to finish current and resistance today, and we can continue electromotive force on Thursday for the next lecture. So what we have here during that lecture, we have electric current. We will talk about electric current, and we will also talk about how charges move in a conductor. So we will spend a lot of time to understand the flow of the current within the conductors. We will also talk about resistance of a conductor, and we will also talk about resistivity and conductivity. And of course, there is a relation between resistance and resistivity. We will talk about this. And next lecture, we will see electromotive force makes possible for current to flow in a circuit. And we will also see energy and power. You remember during the last lecture in capacitance, in capacitors, we have discussed energy and power of charges produced by charges. Again, during that lecture, we will also see how to calculate energy and power in circuits. And we will also try to understand the flow of current in metals. So this is the content of chapter 25. It is very nice lecture and contains basic information to understand forthcoming lectures of this physics 2. So during the last 4 chapters, we have seen charge, we have seen electric field, we have seen electric potential. So we have seen Gauss law, right? And also we have seen capacitors. So during last 4 chapters, we studied the interactions of electric charges at rest. This is very important. Charges at rest. So we have considered metallic sphere, or we have also considered metallic cylinders, okay, or wires, but we have considered that charges at rest. This is very important. Now we are ready to study charges in motion. Now charges are traveling within the material. So this is the main difference within that chapter. So electric current consists of charges in motion, from one region to another within the material. So what is electric circuit? If the charges flow a conducting path that forms a closed loop, the path is called an electric circuit. We will go into detail. So we will also see this one. And we will talk about the energy of the charges that decreases as the current flows through light bulbs. For example, here you see flashlight on the hand of this child. So there's a light here. So where does this energy come from? Okay, there's a battery within the flashlight, and this energy decreases as the current flows through light bulb here. And what is the importance of that chapter? So this is the basic of more or less all other forthcoming chapters. Circuits are at the heart of modern devices, such as computers, televisions, integrated circuits, industrial power systems. Every modern devices contain that integrated circuits. Okay, so now let's start with the moving of charges within a conductor, or drift of moving charges. Do you know the meaning of drift? So the word is important, drift of moving charges. here we have a metal, okay, conductor without internal electric field. Here we have negative charge. You can see this is a conducting wire, and there is no electric field. So what is the behavior of this electron within this conductor? What kind of movement we have here? So here you see path of electron without electric field. So this blue curve or blue path here, okay, blue path tells us the path of electron without electric field. So it is scattered within the crystal. You see, within the conducting material, it is scattered. Okay, it goes everywhere. So like this. So this type of movement within the conductor electron has. So, but what do you see here? This is the first position of the electron, and this is the final position, P2. So there is no huge difference between two positions. But what happens if we apply electric field? So in this direction, for example, here we have same conductor with internal electric field. Now we have electric field in that direction. Can you see that? So since we have electron here, there will be force acting on this electron due to the electric field, okay? An electron has a negative charge Q, so the force on it due to the electric field is in the direction opposite to electric field, okay? So due to that force, electron has two types of movement. Don't forget this. The first one is the previous movement without internal electric field, and now we have another movement due to the electric field. So as a result, we have a red curve here, okay? Scattering of electron or a moving of the electron within the conductor shown by the red curve here. So it is scattered from that position, scattered from that position, so scattered from that position, scattered from that position. But you see here that there is a net displacement along the wire here. So electron is moving in that direction. Compared to the without internal electric field, we have net displacement. And this displacement, so this was the position one, this is the final position with the electric field, okay? So the displacement between two positions without electric field, with electric field, which is given by velocity of electron, which is called as drift velocity. You can see subscript D, drift velocity of electron, and this is delta T, time interval. So the electric field results in a net displacement along the wire. So what about the velocity of electron in a conductor? The random motion of electrons has a very fast average speed of 10 to 6 meters per second, okay? We are talking about this random motion of electrons in a conductor, 10 to 6 meters per second. So what is the drift speed? Drift speed is very slow compared to the random motion of the electrons. And this is on the order of 10 to minus 4. Can you see that? 10 to minus 4 meters per second. So far, I think it is enough to discuss the drift of moving charges. So now let's a little bit go into detail about the drift of moving charges. So what happens here within the conductor if there is an electric field? Electric field does work on the moving charges, okay? So there is a net displacement of the moving charges. So electrons get some extra kinetic energy, right, due to the electric field. So this kinetic energy is transferred to the material of the conductor by means of collisions with the ions. So you can see that. Let's consider that this is the inner part of the conductor, and electron is scattered everywhere, okay? Makes collision ions within the conductor material. So due to that collisions, this kinetic energy of the electron is transferred to the material of the conductor. Okay, so this produces a vibration about their equilibrium position. So a vibration of the ions within the conductor. So this energy transfer increases the average vibrational energy of the ions and therefore the temperature of the material. So if you apply an electric field due to the movement of the electrons, okay, since the kinetic energy is transferred to the material of the conductor, temperature of the material increases. Okay, temperature of the material increases. This is very important. So kinetic energy is transferred to the material as a temperature. So this is very important. So of course, some part of energy is also used to move the electron in certain direction, but much of the work done by the electric field goes into heating the conductor. This is the mechanism of drift of moving charges. Any question in that point? If you have, okay, then let me continue. So signs of the charge carriers. So here we have seen that within a conductor, charges are electrons. Okay, so but this is not the case always. Sometimes in some conditions we have different charge carriers. So sign of charge carriers are very important. So the charges of the moving particles may be positive or negative depending on the material. Here I will show you some different materials. For example, metals, we will talk about plasma or an ionic solution. For example, here there is an ionic solution. I will go into detail. And in a semiconductor material, metal, plasma, ionic solution, semiconductor. So depending on the material, charge carriers are changing. So in metals, as you know, the moving charges are always negative electrons. So, but in ionized gas, for example, in plasma or an ionic solution here, the moving charges may include both electrons and positively charged ions. So charge carriers are doubled here, not only electrons, but both electrons and positively charged ions considered as moving charges. In a semiconductor, the situation is a little bit different. For example, germanium or silicon, conduction is partly by electrons and partly by motion of vacancies. So what is vacancy? Vacancy is also known as hole. Okay, in Turkish vacancy, boşluk. Hole is also boşluk. Okay, so you take one electron from the atom, for example. So there is a positively charged place. You can consider like this. These are sites of missing electrons and act like positive charges. Okay, holes within the semiconductors or vacancies are considered as positive charges. Okay, this part is important. So we know electrons, they are negatively charged, but vacancies or holes are considered as positive charges. So in semiconductors, there is a term like this, majority of charge carriers. So we have electrons and holes, I mean positive charges and negative charges, but what is the majority of charge carriers? So negative charges are, we have more negative charges or we have more positive charges. It depends on the material, okay? For example, if majority of carriers are electrons, this type of semiconductors are called as N-type semiconductors, this letter N, okay? And if the majority of charge carriers are positive charges, I mean holes, then this type of semiconductors are called as p-type. So this is not the discussion here, but I wanted to tell you this information also. So let's look at that one. This is an ionic solution. This is salt, you know, salt, okay? And there is an ionic solution. Salt is formed from sodium ions and also chlorine ions. So part of electric circuit that includes this light bulb here passes through a beaker with a solution of sodium chloride, salt. So the current in the solution is carried by both positive charges, positively charged sodium ions, and negative charges, chlorine ions. Okay, this is very important. So not only negative charges or not only positive charges carry the current here. Both of them carry the charge within that ionic solution. Any question also in that part? If not, I would like to continue. So now let's talk about direction of current flow. So this is also very important basic information. So a current is any motion of charge from one region to another. So we are talking about current. What is current? Current is movement of charges from one place to another place, okay? So, but what about the direction of the current? In that direction, in that direction. So a current can be produced by positive or negative charge flow. We have already discussed in the previous transparencies. But conventional current is treated as a flow of positive charges, okay? So here you see a conductor. This is the direction of the electric field. Can you see that? Direction of the electric field. So from positive to negative. So here we have positive charges. All of them are positive charges, many positive charges. So there is a force acting on each positive charge due to the electric field. So each positive charge has certain drift velocity, okay? Again, along the electric field. So the direction of the current is along the electric field. So current is treated as a flow of positive charges. So positive charges are moving along the electric field. This is the direction of the current. Direction of current is always along the direction of the current, and we consider always direction of, or flow of positive charges. Don't forget that information. So now let's consider metals. In metals, the charge carriers are electrons, right? Negatively charged electrons in metals. So what about the direction of the current in metals? The moving charges are electrons in a metallic conductor, but the current still points in the direction positive charges would flow. Okay, so again, the direction of the current, look at that point, is along the direction of the electric field. So here we have negative charges. Due to the electric field, there will be force opposite to the electric field, and we will have drift velocity again opposite to the electric field, but the current is along the electric field, since the conventional current is treated as a flow of positive charges. Okay, so if you put positive charges here, the flow will be from that point to that point along the electric field. Okay, so for this reason, we consider that the current is along the electric field. Okay, now let's try to calculate what is current and how to calculate it. So the current through the cross-sectional area A is the net charge flowing through the area per unit time. Now let's look at that figure here. There is a light bulb here, and there is a conductor, okay? And here we have a battery. This is negative side of the battery. This is the positive side of the battery. And current flows from positive to negative. Okay, this is the direction of the current flow. So now here we have a conductor. I will magnify it. So if I magnify it, I see like this. Let's consider that the carriers are positive charges here. So this is the direction of the electric field. This is the direction of the current. And these are positive charges. This is drift velocity along the electric field because we have positive charges. So now I choose a very small disk here, okay? So this is the area of the disk, and this is the width of the disk. So what is this? Velocity times time. This gives us distance, okay? So displacement of the positive charges. So the current flow within that material is given by net charge dq flows through an area here in a time dt. Okay, net charge flows through this area in a time dt. This is the current. Any question here? If not, I will continue. Okay, now what is the unit of current? SI unit of current is ampere. Okay, so you know the unit of charge, coulomb, this is second, right? Coulomb per second. 1 amp is equal to 1 coulomb per second. And the name comes from the French scientist, Henri-Marie Ampère. And now let's try to compare the currents depending on different instruments. For example, flashlight, in Turkish fener, the cell size. So the current in the flashlight is about 0.5 to 1 amp. The current in the wires of a car engine's starter motor is around 200 amps. And the currents in radio and television circuits are usually expressed in milliamperes or microamperes, and the currents in computer circuits are expressed in nanoamperes or picoamperes. Okay, very small currents in computer circuits. And unit is ampere. So now here we have current, but here we have drift velocity. So is there any relation between current and drift velocity? How to get this relation? I will try to do that. So suppose that there are n moving charge particles. Here I will try to show you. One moment, please. So here I have n moving charge particles per unit volume. Here we have many charge particles, okay? But in unit volume, I consider that there are n moving charge particles, okay? In a time interval dt, each particle moves a distance velocity times dt, drift velocity dt, okay? This is let's say displacement along the x-axis, okay, which is given by drift velocity dt. So here we have, okay, so what is the volume of this disk? The volume is drift velocity times dt times area here, okay? This will give us the volume of the cylinder. So volume of the cylinder is given by area of the cylinder here, right? Area of the cylinder and thickness of the cylinder. Thickness of the cylinder is given by that expression. displacement of the charged particles. So now let's try to calculate how many particles, how many charges do we have within that disk or within that cylinder. The total number of the charges here, given by n times volume of this cylinder. Okay, so in unit volume we have n charged particles. This is the volume of the cylinder. If in a unit volume we have n charged particles, then within that volume of the cylinder we have n times volume charged particles. Then we have found the total charged particles within that cylinder. Okay, so now we know the number of the charged particles. So let's try to calculate their charges, total charge included within that cylinder. The total charge or net charge within that cylinder is given by dq, that flows out of the end of the cylinder during time dt. So each charge within that cylinder has q charge, and we have this number of charges. Each have q, and this is the number of charges within the cylinder. Then the total net charge within that cylinder is given by n q v d a dt. What is n? Number of charges in unit volume. This is charge of each particle. This is the drift velocity. This is the area of the cylinder or area of the cable you can consider. And this is the time interval. This is the net charge flows within that cylinder. So that's fine. So what was the current? Current was dq over dt, okay? Then by using that relation, I can calculate current. So put that relation here instead of dq. Then here we have dt. This dt will cancel this dt. Then here we have relation for the current. So now we have current depends on number of charged particles per unit volume, the charge of each particle, drift velocity, and area of the cylinder. So now we have relation between drift velocity and current. So nice. Then maybe you have question. If you have question, you can ask if something is not clear. So we continue with the current, drift velocity, and current density relation. So what is current density? Here we have current, okay? So what is current density? The current density is given by current per area, okay? Current per area is called as current density. For example, here, what you see that here we have very small cables. Let's consider very small cables. And here we have a big battery. So area of the cross-sectional area of the battery is higher than the cross-sectional area of the cable. Okay, so they will have different current density. So look at that one. Current density is current per area. So this area will cancel this area here within the current. Then the current density J will be shown with that expression NQVD, number of charged particles in unit volume, the charge of the particles, and drift velocity of the particles. So what is the unit of that current density? This is ampere. This is the meter square, ampere per meter square. So here we have one more information. If moving charges are negative rather than positive, okay, so here we have discussed positive charges, but what happens if these positive charges are negative? I mean, if we have charge carriers, if we have electrons as charge carriers, then the drift velocity is opposite to electric field. So this is the direction of the electric field, okay? And we have positive charges. Then the force due to the electric field acting along the electric field, then the direction of the drift velocity and electric field are same. But if we have electrons, the force will be like this due to the electric field, then the drift velocity will be opposite to the electric field, okay? So the drift velocity is opposite to electric field if we have negative moving charges. But the current is still in the same direction as electric field at each point in the conductor. Hence, current and current density don't depend on the sign of the charge. So let me explain this part. It is very simple to understand if you can concentrate. Look at that formula. This is the current formula. This is the N, this is Q, this is drift velocity. So if the charges are positive, okay, the drift velocity is along the electric field, like this. The drift velocity is along the electric field. Let's choose that direction is positive, okay? So positive drift velocity and positive charges, then we have positive current. So current is along the electric field. So if you have negative charges, the sign of Q is negative, but the direction of the drift velocity is opposite to the electric field in negative case. So in the opposite direction. So you can also consider that this is also negative. Negative times negative. Again, current will be positive along the electric field, okay? The same situation happens also for the current density. Here we have Q and V, the drift velocity, okay? This paragraph explains this mechanism. So now we have here, so we can replace this Q charge by its absolute value, okay? Since the current density and current don't depend on the sign of the charge, they are always along the electric field. So then we can have that relation. This is current, dq over dt, and qvda. So here we have charge per particle. Okay, but of course there's a difference between current and current density. So we can define a vector current density that includes the direction of the drift velocity. So current is not vectorial. Don't forget, I will talk about this, but this current density is vectorial. This is not vectorial, this is vectorial. Don't forget this. And since this is vectorial, this vector current density, we can show this one by the direction of the drift velocity, this vector, okay? So again, I would like to remind you that the vector current density is always in the same direction as the electric field. So this J is always along the electric field, no matter what signs of the charge carriers are here. Here we have positive charges, and drift velocity is along the electric field. So positive charge, drift velocity is along the electric field. So current density is also along the electric field, okay? But if we have negative charges here, drift velocity will be opposite, negative, opposite, and negative opposite will give us positive, again along the electric field. So the time is almost finished. Now we have 37 minutes. Okay, I will continue until it stops. So if it stops, we will continue at 11:30. Okay, now it is 11 past 7. So, sorry, 7 past 11. So if it stops, I will continue with 11:30. Don't forget, they will restart at 11:30 when this stops. So let's continue as much as we can do. So we have finished that part. So now let's compare the current density and current. So the current density is a vector, but current is not. So what else I can tell you here that the direction of the current comes from positive to negative, okay? And within that circuit, everywhere current is constant, okay? Everywhere current is constant, but the current density is not constant everywhere. Its direction changes. Here, the current density is going down, but here, current density is going up, okay? In addition, what we see here, the current density is given by current per area, right? So the cross-sectional area of this wire is much smaller than the cross-sectional area of the battery. Since current is constant, here we have small area, big current density here, but here we have small current density since the cross-sectional area increases within the battery, okay? So don't forget this difference between current density versus current. So let's try to continue with that example from the book. This explains current density and drift velocity in a wire. So we have a copper wire here, 18 gauge. 18 gauge is a coding number for copper wires. So the size usually used for lamp cords. This has diameter of 1.02 millimeter. This is so you can consider that this is copper wire, and diameter is given within the question. This carries a constant current of 1.67 amp to a 200 watt lamp. The free electron density in the wire is 8.5 times 10 to power 28 per cubic meter. What is free electron density in the wire? Copper is metal. So in metals, the charge carriers are electrons, right? Free electrons. The free electron density means that number of electrons in unit volume, namely this number here, N, okay? Number of electrons in unit volume. It is also called as free electron density, okay? So now we have two target variables, current density, what is current density, J, and what is the drift speed. So the current is given, okay? In order to calculate current density, you need area. You can calculate area. Here, the diameter is given. You can calculate radius, or you can calculate like this. Calculate area, put the area here, current is given, and then you can calculate current density ampere per square meter. So what was the second question? What is the drift speed? So J here is given by that expression, current density, NQVD. So N is given, okay? So J is calculated, Q is given, then you can calculate, this is the charge of the electron, Q is charge of the electron, and drift velocity is asked. So this is calculated here, put it there. N is given here, put it there, okay? Then this is the charge of the electron, and you can calculate the drift velocity 0.15 millimeter per second. So the electron within that copper wire travels with that speed, 0.15 millimeter per second. So let's continue with resistivity. So what is resistivity? You can consider like this. So let's consider that you would like to flow charges through that material from that point to that material to that point. So this material resists against that charge flow. Okay, this is the resistivity of a material. You can consider simply like this. Okay, but resistivity of that material, are different from each other. So we will talk about this. But in mathematics, we can consider like this: the resistivity of a material is the ratio of the electric field in the material to the current density it causes. This was the electric field, magnitude of electric field in material. This is the magnitude of current density caused by the electric field. This is the resistivity of a material, electric field over current density. This is resistivity, and there is another term, conductivity. Sorry. So the conductivity is the reciprocal of the resistivity. So if the resistivity is high, then the conductivity is low. If the resistivity is low, then the conductivity is high. You can consider like this. So what is the unit of resistivity? The unit of resistivity you can calculate easily. Remember the electric field. Electric field is given by volt per meter. Do you remember this one? Let me remind you here by using that color, for example. Electric field is given by volt per meter, okay? So you remember that one. So the current density is also given by that expression, okay? Current per area, amp per meter square. So this is volt per meter, okay? So if you put volt per meter for the electric field here, and if you put ampere per square meter instead of current density, then the unit of the rho is given by that expression, volt times meter per ampere. So what do you see here? Volt per ampere. Volt per ampere is called as ohm, 1 ohm, volt per ampere. So here we have meter. Then the unit of the resistivity, ohm times meter, or ohm meters, we can consider like this. So a perfect conductor would have zero resistivity or very low resistivity. So, and a perfect insulator would have an infinite resistivity. Metals and alloys have the smallest resistivities and are the best conductors. The resistivities of insulators, this is very important, are greater than those of metals by an enormous factor on the order of 10 to the power 23. So here I will show you, let me allow newcomers. Okay, now here we have list of resistivities at room temperature for some materials. Here we have copper, gold, lead, pure carbon, graphite, glass, Teflon, and wood. This copper, gold, lead, iron, okay, these are conductors. And what do you see here? The resistivity is given by 10 to minus 8, very low resistivity in copper, gold, and lead because they are conductors, okay? So, but in case of semiconductor, for example, graphite here, the resistivity increases, okay, up to 10 to minus 5. But in case of insulators, resistivity goes to 10 to power 14. Huge resistivity in insulators, in glass, in Teflon, in wood. So the resistivity is huge in insulators. So can we use them? Can we use that property of insulators? Of course, everywhere in industry, in technological devices, this huge resistivities of insulators are very useful. I will talk about this. So here we have an example. This is an integrated circuit. You can consider a board in computers, okay? This blue color here, okay? You can consider an insulating board made from insulating material. And here we have conducting paths, okay? Or traces, conducting paths. Many conducting paths we have here. So the distance between two paths is very small, but even with very small distance, there is no connection in between due to the good insulator of that material. So the copper wires on this circuit board are printed directly onto the surface of dark colored insulating board. Even though the traces are very close to each other, the board has such a high resistivity that essentially no current can flow between the traces. So without using insulating PCB, insulating material, you cannot produce an integrated circuit boards. So these are the lines, and there is no electrical connection between the lines due to good insulating property of the substrate, we can say. So here we have another application, biological application, resistivity and nerve conduction. This is the image from an electron microscope, shows a cross-section through a nerve fiber. So let's consider that this is the nerve fiber. So you can consider it goes from that region to another region, okay, very long one. And now we are looking from the cross-section, okay. So what we have in the cross-section of the nerve fiber, we have axon in the center, and we have myelin around the axon. So a nerve fiber about 1 micron in diameter. So the diameter of this one is about 1 micron. A layer of an insulating fatty substance. What was fatty? Okay, so we have discussed this one during the last lecture. Yağlı bir doku in Turkish. A layer of an insulating fatty substance called myelin. Myelin is insulating material here. Okay, this is wrapped around the conductive material of the axon. Axon is conductive. This is insulating. Okay, the resistivity of myelin is much greater than that of the axon. So an electric signal traveling along the nerve fiber confined to the axon. This makes it possible for a signal to travel much more rapidly than if the myelin were absent. You can consider like electric cords, okay? Just consider this electric cord. This plastic is insulating, and there is a metal wire which is conductive within that plastic cord. So it is same also in the nerve system, human nerve system. So very nice example, insulating material and conducting material. So now let's discuss the resistivity versus temperature. So this is the resistivity, this is the temperature. So let's consider that this is metal wire, okay? So I heat that metal. So what happens to the resistivity? So this is the question. So here you see 0 Kelvin, this temperature in Kelvin range, from 0 Kelvin to the room temperature, higher temperatures. This is the resistivity of a metallic conductor. This is resistivity y-axis. This is the temperature. So what do you see here, that if you increase the temperature, resistivity of metal increases. Resistivity of that material increases if it is metal, and if you increase the temperature of that metal. So as temperature increases, the ions of the conductor vibrate with greater amplitude, making it more likely that moving electrons will collide with ions. So if you heat the metals, the electrons will collide with the ions within the metal. This impedes the drift of electrons through the conductor and hence reduces the current. So you will increase the number of the collisions within the metal if you increase the temperature. This is the main idea behind this. So if the collisions are increased, then the resistivity is increased. So conductivity goes down at higher temperatures. But the strange thing is that here we have more or less linear behavior. I mean, you increase the temperature and then resistivity goes up. But here we have more or less a constant region at low temperatures. Can you see that? If I magnify that region, you can see like this, conductor at low temperatures. But you see here that we have different behavior. So this resistivity versus temperature can be explained with that formula. This is resistivity at certain temperature. For example, you are looking for the resistivity at that temperature. Resistivity at that temperature. So we need resistivity at certain temperature. So this is given by 1 plus alpha temperature of that position and minus temperature of this guy, okay? So what is this alpha? Alpha is temperature coefficient of resistivity. For metals, this alpha is positive number. So just look at the formula. It is very easy to understand. Normally, at low temperature, this metal has ρ0 resistivity, okay? And now I increase the temperature. What do you see here? That since the alpha is positive for metals, this term is increasing. It goes up. Then the total resistivity increases. Okay, you can see it here. So in semiconductors, this alpha is negative. Then if you increase the temperature, this goes down and this goes down. I will go into detail. Do you have any question here at that position? Okay, then let me continue. So what about semiconductors? But let me also remind you that the application of that property of the metals, this is very important. So the resistivity of graphite, for example, here decreases with increasing temperature. This is the resistivity of semiconducting material. This is the increasing temperature. But you see here that at low temperatures, resistivity is huge. It goes to infinite, okay? But whenever we heat the semiconducting material, resistivity goes down and then conductivity increases. Semiconductors become more conductive at high temperatures, okay? The mechanism is here. Alpha is negative for semiconductors. If you increase the temperature, this negative number increases, and then here we have negative, here we have positive. This goes down, okay? This goes down like this. So resistivity decreases with increasing temperature in semiconductors. So what do you see here? At high temperatures in semiconductors, we have more or less constant resistivity, okay? Here, resistivity at low temperatures changes a lot. With temperature, resistivity changes a lot. Here, for the metals, resistivity changes a lot at high temperatures, but low temperatures, it is more or less constant. Here, for the semiconductors, completely different. So what is the practical application of that property? Semiconducting materials are usually used as temperature sensors at low temperatures, okay? For example, you would like to produce a device in the satellites or in the laboratory, for example, you would like to measure temperature at low temperatures. So since the resistivity of semiconductor changes a lot at low temperatures, you can use semiconducting material as a temperature sensor. But in case of metals, since they have very nice linear curve or more or less, not linear, you can consider this type of behavior, but at higher temperatures, resistivity changes a lot in metals. So metals can be used as a temperature sensor in higher temperatures. For example, at 1000 Kelvin, something like this, metals can be used as a temperature sensor. So you would like to measure the temperature at low temperatures and high temperatures. Metals can give you better and accurate results at high temperatures, and semiconducting material can give you better and accurate results at low temperatures. This is the very useful application of resistivity versus temperature. So here I have already explained the mechanism. So metals has positive temperature coefficient. So if the temperature increases, this term increases, and then resistivity increases in metals. Okay. In semiconductors, alpha is negative. Then if temperature increases, this term is decreases. Then resistivity decreases. You can see it here. So what we have here, alpha for different materials. Aluminum is metal, brass is metal, constantan, it is more or less constant, it does not change. Copper is metal, iron is metal. What do you see here? That metals have positive alpha. Here we have graphite, semiconducting material, it has negative alpha. Okay, so easily you can understand the mechanism of temperature coefficient of resistivity. So now let me continue with the superconductors. We have seen metals, conductors. Metals are good conductors, but they are not perfect conductors. So we have seen semiconductors. Now we will talk about superconductors. What are the superconductors? Again, here we have temperature versus resistivity. Remember the metals. Metals like this, if you decrease the temperature, resistivity of metal changes like this, okay? Look at the previous transparency. So let me go back. Can you see that? It goes up if you decrease the temperature. Now let's come to the superconductors. The situation is completely different. What we have here, this is metal. In metal, it goes down. Okay, this is metal, normal conductor. But in case of superconductors, something is changed. Let me clean that part. So first of all, it goes down. If you decrease the temperature, resistivity goes down, okay, like in metals. But at certain temperature, this is also called as critical temperature, TC, critical temperature. So at certain temperature, resistivity of superconductor goes to zero. No resistivity, okay? Resistivity is zero, below that critical temperature. So material in that region is superconductor. So these superconductors are very useful materials and widely used everywhere. We will talk about these superconductors again in chapter 29. I will not go into detail here, but magnetic levitation, fast trains, and also many low temperature devices, also electromagnets in magnetic resonance imaging devices in hospitals, okay, use that superconducting materials, very important materials for industrial and technological applications. So now let's talk about resistance and Ohm's law. So what is the Ohm's law? Ohm's law tells us that rho is constant and independent of the magnitude of electric field. Here we have electric field, here we have current density. So if you increase the electric field, J is also increasing. So it becomes constant. If the material obeys on Ohm's law, okay? Ohm's law tells us that resistivity of a material is constant. It does not change. Don't forget this. So, but what we have here, so I can write this electric field like this. Electric field rho times J, right? This is the resistivity. So since this is constant, if I increase this one, this also will be increased. But it is not so easy to measure electric field. It is also not so easy to determine the J. Instead of J, I can use current. Instead of electric field, I can use voltage. I can measure them much easier compared to J and electric field. So this is the material. This side has higher potential, lower potential. This V is the potential difference between two ends. Due to the potential difference, there is an electric field within the material, and this is the current density. This is the current of the material, and this is the length of the material. So here, look at that equation again. We know that electric field within that material can be written like this: potential difference over length of the material. Remember that formula. I will write again here. Remember that formula. Electric field is given by V over D, okay, from previous lectures. So D here is the length, okay, and which is given by V over L, and J is current density, current per area. Area is that one, okay? So current is given here. So just take this E, put it there. Just take this J, put it there. Then V over L, V over L, and rho here, instead of J, I over A. So if you take V from that equation, V will be like this. You see, rho L A I. So then resistivity of material, length of the material, this is the current, this is the cross-sectional area, this is the potential difference between two ends of the material. So nice. Then let's continue. What we have here, this term here, rho LA, is called as resistivity. So resistance. This is resistivity, but this term is called as resistance. This is resistivity. This is resistance, shown by capital R. R is equal to rho L over A. So what is L? Length of the material. A is cross-sectional area of the material. So then I can get that expression. Put R here. V is equal to current times resistance of conductor. This I is current in the conductor, and V is the voltage difference between ends of conductor. So now we have relationship between voltage, current, and resistance. So look at that one. Resistivity, electric field over J. Now we have relation, this one. R is given by volt per current. Okay, instead of electric field, here we have volt, much easier to measure. instead of current density, here we have current, much easier to measure. And here, instead of resistivity, we have resistance, okay, which is given by that expression. So I think we can continue if you don't have any question in that part. So now let's talk about resistors. Resistors are used in integrated circuits in electronic devices. There are many different types of resistors, very small things. I mean, the size of the resistors are very small in millimeter. You can see in many electronic circuits and devices. If you open your electronics, you can see this type of resistors. So these resistors are color coded for easy identification to calculate their resistance. So the unit of resistance is given by ohm, okay, volt per ampere, and it is given by ohm. So here we have one example for the resistor color coded. So each color tells us something. This is first digit, this is second digit, this is multiplier, this is tolerance. I will talk about what they mean. So here we have a table. You see that? These are the colors: black, brown, red, orange, yellow. Value of digit, this first digit. So this is second digit. Here we have green color. Look at green. Let me use pen in that point. So here we have green. We have number 5. Okay. Here we have violet, number 7, second digit. Okay. Here we have multiplier. Multiplier is given by the color orange. Value of multiplier is given in the second column, 10 to 3 ohm, okay? Or I can write it like this, 57, sorry, have to delete that part. Okay, 57 kilo ohm, or 57 10 to power 3 ohm, okay? So this color here, this is silver band. Sometimes it becomes gold band, okay? Depending on the color here, you can determine the tolerance of the tolerance and accuracy of the resistor. So it means that 57 kilo ohm plus minus 10%, okay? So this is the color-coded identification of the resistors. Do you have any question here in that part? Okay, then let's continue. I will talk about ohmic resistance. What is ohmic? Ohmic resistance means that resistor that obeys Ohm's law. If you are talking about Ohm's law, I have already told you here that if a material obeys on Ohm's law, rho is constant, okay? This must be constant. Again, if you are talking about ohmic resistance, means that R is constant. Rho, resistivity, or R, resistance, must be constant if you are talking about ohmic resistance. Don't forget. So what we have here, I have voltage, potential difference axis here, and current axis. So this is the slope, 1 over R. It comes from that expression. It comes from that expression. V is equal to, okay. So if you take this one, okay, so here we have the slope, I over V. So what we see here, that if the material is ohmic material, ohmic resistor, then this slope is constant. It does not change because R is constant, okay, in ohmic resistance. Don't forget this. But in case of non-ohmic resistance, something is different. What you see here, this is the voltage, this is the current, and what about the resistivity? Completely different. Here, if I apply voltage in positive direction, okay, in the direction of the positive current, voltage is increases and then current is also increasing, okay? Voltage increases, current increases. But in the direction of the negative current, what you see here, I increase the voltage, but current does not increase. So little current flows. Here, huge current in positive direction of the current can flow easily, but here we have huge resistance against the current. So this is very nice property of the semiconducting diode, which is one example of non-ohmic resistor. Okay, so resistivity changes depending on the direction. So you apply current in that direction, device allows for the current. But when you apply the current in that direction, device does not allow for the current. So it is open in that direction, it is closed in that direction, and they are used in technological applications widely due to that property. So now I have two examples of that part of my lecture. Now we will see electric field potential difference and resistance. So here we have again 18 gauge copper wire. This is the class of the copper wires. Has a cross-sectional area of 8.2 times 10 to minus 7 meters square. We have already calculated in example here in the previous lecture. So it carries a current of 1.67 amp. Current is given, area is given. So what about the questions? Find the electric field magnitude in the wire. Electric field is asked, and the potential difference between 2 points in the wire 50 meters apart. So we have a wire, it is 50 meters long, and the potential difference is asked, and the resistance of a 50 meter length of this wire is asked. So electric field is asked. In order to calculate electric field, I should know resistivity of the material, and I also should know the electric density, right? So current density. So the current density J is given by current per area. Current is given, area is given, put the current and area here, then I can calculate current density. Electric field can be calculated easily, volt per meter. So what was the second question? Potential difference between 2 points in the wire 50 meters apart. So potential difference can be written like this: electric field times length. So length is given, electric field is already calculated, then I can calculate potential difference 1.75 volt. So what is the last question? Resistance of a 50 meter length of this wire. Resistance is asked. Resistance is given by rho times LA. Rho is given, I mean the resistivity of the copper wire. You can find from the tables or usually given in the question, okay? Don't worry about this. So length is 50 meter, area is already given, then resistance for the 50 meter copper wire is 1.05 ohm. You can also calculate this resistance from that formula, V over I. We have already calculated, by using that relation, put it there, and then I is given within the question, put it there, 1.05 ohm. So we have same. result. So don't forget this resistance and resistivity are constant in ohmic resistors. So now we have another example, and this is the last transparency of my talk. We have more or less two minutes. I can finish, I think, within 2 minutes. Okay, let's continue. So we will talk about temperature dependence of resistance within that example. Suppose the resistance of a copper wire is 1.05 ohm at 20 degrees Celsius. Find the resistance at 0 degrees Celsius and 100 degrees Celsius. So we have that relation. This is the target resistance at target temperature. This is the temperature coefficient of resistivity. This is the initial resistance of the material. This is the initial temperature of the material. Okay, so our reference resistance and reference temperature we can see like this. So now we will calculate the resistance at 0 degree Celsius. So put the temperature here, 0 degrees Celsius, put the reference temperature here, 20 degrees Celsius, and the alpha is given in the table, put it there. Normally in the question, it must be given. So then R0 reference resistance is given here. So the resistance at 0 degrees Celsius is given by that expression. It is 0.97 ohm. What do you see here? At 0 degrees Celsius, the resistance is lower than this one. It is 0.97. This is higher than 1 at 20 degrees Celsius, because if you cool the conductor down to low temperatures, then the resistivity goes down, resistance goes down. Okay, it is logic. So if you heat the material, this is the target temperature, 100 degrees Celsius. This is reference temperature. This is the alpha temperature coefficient. And here we have reference resistance given here. So final resistance at 100 degrees Celsius is 1.38 ohm. So if you increase the temperature, resistance increases much higher than the resistance of the copper wire at 20 degrees Celsius. So it is obeying that relation of conductors, resistivity versus temperature relation of conductors. So with that transparency, I finish my lecture today. Next lecture on Thursday, I will continue with the electromotive force and circuits. So if you have any question, I can answer them. Then I will close the session. Any question?
Hocam bu slaytları paylaşma imkanınız yok değil mi?
I cannot share the transparencies, but I'm recording the videos. I will put that videos on my YouTube channel. Then you can watch them again from the YouTube channel. But I cannot share the transparencies. Any other question? Okay, I will share the videos in the YouTube channel, but I don't know whether any copyright issues will be applied due to the transparencies again. We are allowed to use that transparencies because we are customer of the Pearson Education. Okay, these transparencies are allowed for the instructors. So I'm using in the lecture. So I will publish my lecture in YouTube channel, but maybe they will ask me to remove also my videos from my YouTube channel. I'm not sure about this, but until they give me one answer, I will put them into the YouTube channel, and I will keep them there until they ask me to remove them. Any other question? Okay, so enjoy at home, try to study, try to solve the problems at the end of the chapters. Okay, if you have any questions, please write me. We can arrange some other meetings. Okay, if you have any problems or questions, we can solve together. So take care of yourself. Bye bye. Kendinize iyi bakın.